Welcome back, students. Welcome to the session 13 from the playlist of wave optics. The topic is the fringe width, and this session is in continuation of the session number 12, in which we have studied about the Young's double slit experiment. So this was a figure which we have discussed in the previous session. So this is the screen x dash, in which two pinholes were made, and these two pinholes were illuminated by this single source of light, and this source of light has been depicted as S, and this is another screen y dash. So the light waves which are emanating from these two pinholes will form the constructive or this destructive interference at any randomly chosen point P, and the condition for the destructive interference and for this constructive interference is written here on this board. That is the distance of the nth dark fringe. The destructive interference produces dark fringe, so the distance of the nth dark fringe from the center of this screen is given by this formula, that is equal to lambda d in bracket 2n minus 1 divided by 2d, and this is the equation which we have already derived in the session number 12. Similarly, the distance of the nth bright fringe, the bright fringe is formed due to the constructive interference of the light waves. So the distance of the nth bright fringe due to the constructive interference is given by this formula, that is x equal to n lambda d upon d. Now the fringe width is basically the distance between the two consecutive bright fringes or the dark fringes. It is denoted by beta, and this is equal to lambda capital D divided by d, where d capital D is the distance between the two screens and small d is the distance between the two pinholes. Now the fringe width is basically given by this formula, that is it is equal to xn plus 1 minus xn. Now xn basically is what? It is the distance of the nth bright fringe or the dark fringe, and x. So if I put the value of, if xn is equal to n lambda d upon d, then x n plus 1, this will be equal to n plus 1 lambda d divided by d. So if I subtract, that is if I subtract xn from this xn minus 1, then I will be able to get the fringe width beta, and this will be equal to lambda d upon d. So similarly, the fringe width in the case of this destructive interference, or we can say the fringe width in the case of the dark fringe, will be equal to, again the value will be the same, that is lambda d upon d. Now if this entire experiment is submerged in some medium of, say, refractive index mu, then the fringe width is given by if this entire experiment is submerged in a medium of some refractive index, say mu, then this fringe width will be given by lambda d divided by mu into d, where mu is the refractive index of that medium. So this is all I have for this session, that is the fringe width is given by beta, which is equal to lambda d upon d. For the in the case of the bright fringe, the this fringe width is equal to lambda d upon d, and in the case of the dark fringe also, which is produced in the case of destructive interference, the fringe width is again equal to lambda d upon d. So thank you very much for joining this session, and in the next session now I will be discussing about the displacement of the fringe pattern due to the insertion of a transparent thin plate in the path of one of the spherical wave, this spherical light wave. So I will be discussing about it in the next session, and so till then, have a nice day. Bye.